Ooh-wee! I'm Mr. Meeseeks. Look at me. But today on SDL, Russ is off in Canadian land, I think, eating poutine and Tim's coffee. And I am at another event, and I couldn't be here, so I recorded this for you from the secret lab facility. On SDL, we're going to talk about NAT, the mysteries and mysterious protocols that allow us to beat the odds and avoid IPv6 for as long as possible. So stick around.
This is a Security Weekly production.
Welcome to Secure Digital Life. If your users are going to keep putting risky stuff on your machine, you're screwed. So, Top can help us understand the complexity of blockchain.
I was reading through the show notes, man. Oof.
In binary, it would be 001. Who cares? But it's probably not significant anyway. Be like you're looking out through the HAL dot, you know, like,
oh,
hey Dave, Dave.
It's like Sims, but with, you know,
it would be like Sims
instead of AI. It's only.
Roger Williams University is a premier destination for cybersecurity, offering in-person and online classes designed and taught in collaboration with industry experts. Using virtual environments that simulate real-world systems, you'll solve complex cyber issues and analyze cyber threats to prepare you for in-demand jobs in this rapidly growing field. Whether you're just starting out or want to advance in the cyber profession, RWU offers degrees and coursework at all levels. Learn more at rwu.edu/cyber. Accredited by Microsoft, Cisco, NetApp, IDLE, Oracle, and EC Council, QuickStart delivers high-impact, low-cost IT training through its cognitive learning platform in multiple domains. With QuickStart, you get an ever-growing catalog of courses, self-paced courses offered through a monthly subscription, virtual classrooms offered through an annual subscription, peer-to-peer learning, mentoring, official courses, certified instructors, hands-on labs, and more. For more information, visit www.quickstart.com. Use coupon code PAUL20 to get 20% off on all cybersecurity courses. QuickStart, creating world-class technologists.
Go to IT Pro TV, Security Weekly, /Security Weekly, and use the code SECWeekly30 to try it free for 7 days and receive 30% off your monthly membership for the lifetime of your active subscription. Check out our on-demand material. You really should check that out. Some of our previously recorded webcasts are now available on demand at securityweekly.com on demand. Ticket sales are open for the Social Engineering Rhode Island Conference Saturday, June 16th at Salve Regina University in Newport, Rhode Island. Beautiful Newport, Rhode Island. It's in a mansion, really. Like it would be creepy if it wasn't nice, but it could be creepy. It would be cool if it was creepy, but it's not. It's a really nice place. It's hard to believe there's a university in this mansion, but it is. So check that out. Go to http://se-ri.org. Ooh, that's fun to say. se-ri.org to register for that conference. They still have tickets available. We are giving 2 tickets to this conference. There's some stiff competition, though. I'm not going to make any jokes there. I'm not. There's some stiff competition for this. If you want to make a meme of Paul and Larry and send it to psw@securityweekly.com, we will throw it into the pool of cool memes that we've gotten of Paul and Larry, some of which were rather exotic. And be happy to consider those to see if we want to give you a chance to get some free tickets to the Salve Regina Social Engineering Conference. And this is not a trick, I promise. How do you feel about user and entity behavior analytics? What about your SIEM? SIEM? I don't know how you pronounce it. S-E-I-M. Check out Logarithm's webcast on June 14th at 3 to 4 p.m. So if you want to check that webcast out, you can find out more about SEIM. I think I've always said it SEIM, but I don't know. I heard there were some people at RSA that were saying, like, I can't remember if they were saying seam or sime, but they had some kind of meme about it, and they had a shirt or something. Yeah, it obviously didn't work very well because I don't remember it, but, you know, regardless. Okay, so, the border. Run for the border, SNAT and PAT. So NAT is a Network Address Translation Protocol, and we've had NAT around for a long time, but they really started implementing it in the early part of the 21st century. It's kind of creepy to say stuff like that now. Back in the 20th century. But they started implementing this in the actual firmware and flash or whatever of different devices. It had not been there before. And what the problem was, and this problem started back really in the 90s, where we started realizing that there were only so many IPv4 addresses out there. And what you have to understand is that in the 1990s, there were about 19 people using the internet. And nobody really was thinking about, you know, we've got 2 to the 32nd minus 1 possible addresses out there in IPv4. And I know there's restrictions, and I know there's these reserved for that, but just in general, there's 2 to the 32nd minus 1 addresses out there in IPv4. And basically by 2015, they were all pretty much issued. So ARIN, which is the body that governs IP addresses for North America, had issued all of their remaining addresses by then. So, you know, yeah, we all heard that, and everybody was all freaking out. And, you know, it was one of those kind of vaguely end-of-the-worldy sort of thing. The solution to that IPv4 problem then had 2 approaches, basically. One of them was obviously IPv6. And IPv6 was this, like, really cool idea where instead of 32 bits, why don't we take 128 bits? We're going to make the biggest address space imaginable. And again, today I was saying, you know, I probably back in 95 or something was talking about IPv4 and saying, yeah, we'll probably never run out. I'm not saying that anymore. So I stopped saying we might run out or we probably never run out. But IPv6, which is a 128-bit address space, it's something like 4 undecillion, whatever even that means. It's like some gargantuan number. You know, like more addresses than all the grain. If we give an IP address to every grain of sand on the earth, and you go, so we'll never run out. I don't know about that. Because I do see a day coming when we have like every single hair on our head is got like an IP address, because that way, you know, you can keep up with it. Or you know, the fibers in your clothing all have IP addresses so that you can address, you know, you can change the colors of your shirt, or you can, you know, change the features of your clothing as you walk around. So who knows? Maybe you know, another 20 years from now, well, I'll be going, yeah, okay, whatever. But IPv6 was not popular, and please don't start flaming me over that. I'm not saying it's not good. I'm just saying it was not popular. They're 2 very different things. Like Zima was not good and not popular, but IPv6 is good. It just wasn't popular, and it wasn't popular because it was complicated and scary looking. It had poor marketing behind it because it's written in hex. It's this big, massive, long address strings, and yes, I know there's all kinds of shortcuts, and I have no problem with IPv6. I think it's awesome and cool, but it just didn't catch on. And at the same time that IPv6 was sort of starting to evolve, what happened was the protocol called NAT was made available, and NAT, which stands for Network Address Translation, became this kind of option that people could use to fix up their networks. So NAT has several different features to it, but the one I want to talk about to you is called, or 2 I'm going to talk about, are called SNAT. So SNAT is the first of the protocols that we want to mention that come out of NAT. It did not necessarily solve the whole problem, but it did solve some of the problem. So a little more history. So back in the late 90s, early part of the 21st century, basically everyone was using flat networks, which means that they were not using switching, they were using hubs, and every device on the network had a public IP address, so a static public IP. I mean, that was just how we did things at that point. Now, this wasn't a big issue because a lot of us had gone out and we got Class B addresses. So when we went and got those Class B addresses, I had one. I mean, I sold most of it off, but it belonged to the university, but I had one, and so that's a 16-bit address space, 65,536 addresses. Wow. And we had, what, 9 things inside the university that needed IP addresses. So, I was like, okay, I'll take a few from here. And then I set up a lab, and my lab had IP addresses, and, I've got, tons of addresses. But what happened was, as that changed, and it changed very quickly, all of a sudden, other groups on campus, other people on campus were coming in and saying, we need this. We need access to this internet thing that you keep talking about. And as that evolved, all of a sudden there were departments that had 24 PCs sitting on desktops that all wanted access to the internet. And everybody already had the PCs, but all of a sudden they wanted to network them, which meant our life got a lot more complicated in the networking world. So NAT provided a pretty good solution to this problem, because what happened with NAT was that, look, static or SNAT is available. So all I have to do with SNAT is define a border, and a border, if you don't know, is the place where you touch something else. So that's how I define it. So where my control or custodianship or whatever you want to call it ends, that's where the border of that network resides. So if you're at home and you're using Soho equipment, that border is probably with your ISP. So you've got a cable modem or something, and where that cable modem connects to your system is where your border is defined. And you probably have NAT being used right there. At an enterprise, you may have multiple borders, but you probably have a border where you go out into the public space. Well, in this early model, SNAT said, I can take an address and I can equate it to another address that's inside my network. And this is the basis of NAT. And so static NAT, which is what people call SNAT, they never call it SNAT, which just sounds really awful. Like, he had a big bag of SNAT and it broke open and the SNAT went everywhere, and people were running and children were screaming, and they couldn't clean the NAT up no matter what anybody did, and the NAT just now I'm doing Rick and Morty, right? So that sounds like interdimensional TV show. And the SNAT went everywhere, and nobody could control it. And then some of it got on my hands, and I couldn't get it off. And then it started growing, and the SNAT became it. Yeah, okay, I'm gonna stop doing that now. But you get the idea. So remember, if you go back to your IPv4 lessons, that there are private address spaces inside of IPv4. I mean, think about that. So there are 3 specific ones, and I know there's a lot of other sub-details here that I'm not really getting into because they're not really germane to this. But there is the 10.0.0.0 and the 10.0.0.0/8, the 172.16/16, and the 192.168.0/24. So those were 3 by spec IP address spaces that were set aside as private. They can't be used on the internet. They're blocked everywhere. So if you try to use those addresses and you go out on the internet, they're eventually going to get filtered. Everybody's pretty much that's got any sense is blocking those kind of addresses at their borders. And so you could use those addresses. What that meant was, if I just looked at, and remember, I'm talking about 1999 now. If I just looked at the things I had that needed to get on this brand new, funky, shiny interweb thing, it was probably very limited. So in 1999, I had a couple of servers, a bulletin boarding system, and I had something, there was actually some other systems on campus, but we ended up with maybe 8 or 9 things that actually were on the internet. And all these other people that were wanting to use the networking, because mostly what those people were wanting to use the network for was they wanted to be able to share printers, they wanted to be able to share files, and do presentations and things. They didn't even know what the internet actually was at that point. there was no streaming video or porn or any of that kind of stuff at that time. So what those people were doing was we could just wall them off in this private address space. So I took a 10.1.1 or a 10.000/8 address space and started subnetting it. And so I defined all these subnets for different rooms and different labs and different features and all these things. And I built out that portion of it. That didn't go to the internet. Those people couldn't even get on the internet because there was no way for them to do that. But I took my servers, I took a few other devices that we had, and we set up SNAT. So that meant that I took an address like 10.1.1.80, and I assigned it to a public side of the address like 8.8.8.80. I'll use Google's address space. And come get me, Google. You know where I am. Yeah, they're listening too right now. Yeah, Alexa just lit up and there's like tendrils coming out of it. Yeah, exactly. But that problem, that patched this whole problem very quickly. All of a sudden, I didn't actually need all those addresses. And so we literally started selling off chunks. Now, part of that became what is called classless intradomain routing as well, which meant that no longer was Aaron going to enforce this idea that, a university has a Class B address. Only governments and large corporations who have paid us lots of money get Class A address structures. They started saying, who cares? No longer will you be identified with your prefix on your IP address. So, for the moment anyway, in 1999, 2000, the problem was solved. Very quickly after that, we started having people wanting to connect to the internet. And initially, it was a very few people. So, we got the computer science people, or we got somebody from the IT group or whatever said, can I get on this internet thing? Because I've heard there's useful articles out there scattered amongst the video. That's a joke. There was very little video on the internet at that point. But basically what happened was, at that point, I had tons of addresses. And I was able to go, okay, fine, just take one. I'll give you an address. And so, quickly we were doing that. And I was doing it all with SNAT. Now, as you might guess, before very long, so by around, 2003, 2004, all of a sudden the interweb started being a lot more interesting to people. People found out that you could do ASCII2 porn. I'm not even kidding. I mean, you want to talk about pathetic. ASCII2 porn, if you don't know what that means, don't look it up. You'll be sorry. There were people doing ASCII art, where they literally drew like pictures using like pound signs and @ symbols, and yeah, I mean it's amazingly creative. There was actually pornographic material being distributed through this system called UU encode, UU decode. UU encode, UU I shouldn't get sidetracked by this, but UU encode, UU decode was a way to convert digital files into ASCII files. So it took like a JPEG and converted it into just ASCII characters that could be sent across the interweb. And it was funny. I would get some laughs because people would call me and go, do you know what a UU encoded file is? And they're like, oh, you're looking at porn. And I'm like, no, never. And they're like, right. But all of a sudden, printers, people's desktop computers, started wanting to use the internet. And as that happened, we needed addresses for them. And all of a sudden, I literally went in a space of a few months from we had a complete lid on how many addresses were out there, to people calling and asking for, how do I get on the internet? How do I get on the internet? How do I get on the internet? And all this kept happening, and all of a sudden we were shoveling addresses out the door. And I was setting up a lot of SNATs. And pretty quickly we realized that this was not going to be sustainable. So a new part of the protocol starts to pop up. Now, Aaron had issued all the addresses, so that meant that by 2015, and this obviously we spin forward a little bit, most, if not all of those 4 billion something addresses, 2 to the 32nd minus 1 addresses, had been issued before 2015. And Aaron didn't control everything. There's other entities, but all that, classless interdomain routing, CIDR had helped by allowing people to block out pieces of this. Instead of IBM controlling a whole Class A address, they only got, they could sell off or lease out or whatever they wanted to do. But the idea that all of a sudden we had to still have this one-to-one realm had become very untenable. Now, some of us were using something that's called DNAT. And DNAT was a round-robin way to assign, say, like 10 addresses. So I did this really early, but this was probably like 2003 or 2004. I had like 16 DNAT addresses, and what that meant was 16 people at a time could use the internet. And if you tried to get on the internet and you couldn't get an address, then you just waited and you kept hitting refresh until you got the web page you were looking for. And that satisfied people for about, I don't know, 5 minutes. And so all that really sort of started to fall apart then in the early part of the 20th century. And suddenly we had real issues with it. So I did put, I actually have a Cisco SNAT statement on there to show you kind of how that works. If you look at the show notes for all that kind of stuff. All of a sudden, people at home were getting broadband. All of a sudden, people were, I was getting calls from people in my neighborhood who were saying, do you have a way to get on the internet? That was actually in like 2002, 2003 even. People were starting to get home connections to the internet. They were going to use these connections. They were going to get out in the world. And everything got a little goofy then. And already things like Windows Update were becoming commonplace. You were starting to see, you know, everything wanting to phone home. Your PCs wanting to connect to Microsoft every night and download updates and on and on and on. Today, you know, certainly we start to think about the Internet of Things. We start to talk about what if, you know, my doorbells, my windows, my blinds, my lights, my thermostats, my water heater, my furnace, my air conditioning system, my DMX lights, my, you know, everything in my house is suddenly needs an IP address and needs to phone home. You know, drone swarms, hair on your head, fibers in your clothing, all need IPs, need to get on the internet and phone home. I mean, I know there's all kinds of security issues associated with all that stuff. But as that happened, there just were not going to ever be enough addresses. And that was where IPv6 sort of started becoming this, like, you know, it had been there for a while, but it had started having a little more resonance, and you started hearing people talk about it more at cons. You started seeing cons about IPv6. I know that really, probably, I think it was in like 2002, I went to a training class about IPv6. And none of my Cisco devices at that point supported IPv6. I didn't have any networking devices that supported it. And in fact, I went to this training class and they ran it on like a simulator. And that was because nobody was supporting it. And there was a lot of controversy. Today, you know, pretty much everything supports it. Microsoft enables it by default. So if you're using a Microsoft Windows 7 or later, I think, system, you do have IPv6 enabled. But there was another answer out there that we've already brought up. The other answer that was out there was something called PAT. And PAT stands for Port Address Translation. And what Port Address Translation means is that what if you took advantage of the design of the TCP/IP stack and used that to create a different kind of network protocol? So what happened was, in the TCP/IP stack, there is a 16-bit buffer. And that 16-bit buffer in the stack is for storing the source port for a communication. So this is layer 4, you know, it's really a layer 4 protocol from OSI model. And that is a 16-bit buffer, so it could be anything from 0 to 65,535. So 65,536 possible ports. And they actually have 2 buffers. I think they buffer that separately for UDP, so you could actually have even more than that. We don't obviously use all those. I mean, if you open your computer right now and you do a netstat, you know, -n, you'll see that you have a bunch of stuff open, but you're probably not coming even close to using 65,000 ports. Well, on a router, it was even less. So what if I could use that address space that I've got sitting there, and I could assign all those internal addresses, so the 10.0.0/8 internal addresses, I would assign those to one of those 65,536 ports. Wow. That might be a pretty cool idea. And I could use that address space to make a table of ports, and I could just assign a port to an internal private address. And then what do I do with it on the outside? Well, why not just use the interface address? So if your router has an outside address of 1.1.1.1, why not just use that as the layer 3 address for the public side, and use whatever private address on the inside that you want and equate those two things in a table? And how do I remember it? And so you always have to remember that computers are not necessarily smart, although they're getting smarter, but they're very fast. So what if I've got to create some way to remember this. What if I built a table and I assigned to that, remember, every packet. So every packet, even UDP packets, has a field for source, a 16-bit source port field. So when that packet's created on your machine, it's got a 16-bit source port field. When it goes and it gets moved, it gets changed, it gets modified, it gets shipped across the internet, hop, 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 and ends up in Sydney, Australia, it's still got that source port on it. Because when that transaction comes back, it needs to get back to the source port. Okay, so I've suddenly got a layer 4 OSI protocol that would allow me to take a 16-bit address space of the source and assign it to the IP address, the private IP address on the inside of my system. And I could use that inside address then just internally. So that means if your address internally is 10.1.1.128, I can say in my PAT table, I'm going to assign port 3017 to the IP address 10.1.1.128, and nobody in the outside world will ever see that address. What the people in the outside world will see is they will see 1.1.1.1 with a source port of 3017. All right? For them, that's fine. That means that their reply to, so when you go to a website, their replies, the ACK packets, so that reply coming back is going to go to port 3017, IP address 1.1.1.1. When the router gets it, if it's running PAT, it says, oh, here's something for port 3017. Let me look at my PAT table. Yes, that's assigned to 10.1.1.128. And the ports don't have to be the same. It could be port 80 on 128, doesn't matter. And that equation gets executed. The packet is modified. So the PAT protocol modifies the traffic right there. And it changes it so that it's got the correct internal information. So those packets look different at layer 4 and layer 3 on the inside and the outside. So if you see a router and it's got PAT inside, PAT outside, there's a difference in the inside and the outside of the router, the way the traffic actually looks. So if you Wireshark the outside of your router and you Wireshark the inside of your router, and you can set this up in Packet Tracer, or you can set it up at home or wherever you want to set it up, you can sniff those packets. You're going to see that they're different at both layer 3 and layer 4 on the inside and the outside. And that's what PAT is doing to that traffic. So it's modifying it. Now, that means and leads to, and that's how PAT essentially works. What it means is that you could take a large number of internal addresses and use them with an outside address. Primarily, it means you have to own, maybe, one address. You could literally get away with owning a single external address. Some people don't like that idea. I don't particularly like that, but I also don't have a real giant issue with it, because if the only reason you would want to have multiple addresses is now if you have SNATs. So if you have SNATs on the outside for your servers, you need addresses for those. So you say, I've got a web server. Okay, you need an address. If you have an email server, you need an address. If you have something else, you need an address. So each of those things on the outside of your router are going to have private or public static IP addresses. And you can buy those. I mean, you can, and they're actually, the price on them has come down since this. There was a time when there was kind of a frenzy over, you better buy them now because they won't be around for long, and people were paying outrageous prices for a couple of IPs. But today, you know, I think, you know, you can get one for like, you know, $20, $30, maybe. I think I saw one for sale. I think Cox will give you one for like $20 a month or something like that. You can buy a static IP. For your PAT devices, you may want a separate IP because none of these devices can be accessed from the outside world now. So what that means is that there's no way to get to a PATted device because it doesn't actually have an IP address. And its port numbers are being modified by the PAT algorithm. So you can't do port forwarding per se to get to that device. So what happens then is that when a device that's on the inside, so an internal device, wants to create outbound traffic, PAT is doing that magic and twirling the packet and changing layer 3 and layer 4 for the outside world. That means somebody in the outside world who wants to get to that device that is not a reply is not going to be able to get to it. Now, ACKs work fine. So that means if that device wants to phone home and something be downloaded to it or whatever from Microsoft, that's fine. But someone on the outside can't instantiate a transaction to that padded device. You really need an SNAP for that. There are ways around that. So there are a couple of negatives then with the use of PAT. One of them is that you can't access the internal devices from the outside, which, like I say, that could be a positive thing. I mean, some people say, well, that's great. I don't want, you know, just average people to be scanning my networks, and you can't. The other one is that there's no real clear indication of where the traffic came from if you're out in the world. So if you see traffic coming from 1.1.1.1, yeah, it came from me, but I don't know which device internally actually generated that traffic originally, because the XLate table, which is what that's called, may not persist for very long. So if that person went out and hacked something, 2 days later they get in touch with you and say, what is device 10, you know, what is device 1.1.1.1 with a source port of 3017? And I go, I have no idea. That may have changed 40 times since then. The good news is, of course, you can share all these internal devices on, you know, maybe one outside IP. The obvious question to conclude this, was, does PAT affect performance? And I always get people asking this question, and you say, well, what if you put 65,000 internal devices and they're all going out over the same IP address? Well, the physical bandwidth doesn't change. So whatever physical bandwidth you're using is going to be exactly the same whether you have one person using it or you have 65,000 people using it. Likewise, if you have load balancing, so if you get 10 drops and you have 10 wires connected to the internet, well, okay, you've load balanced across those 10 wires. Adding internal people changes your bandwidth, but it does not change your physical bandwidth. It changes how much is available to each individual user. So if you've got 65,000 people and they're using static NATs or static IPs, nothing's going to change. It just means you don't need all those static IPs. The amount of use is the same. So PAT doesn't affect performance in any obvious way that I've ever seen. It certainly doesn't affect your physical bandwidth in any way. So if you want to drop 65,000 users on a 1 megabit pipe, it's still a 1 megabit pipe. And all of them are having to share it, and it's going to be slow and suck and be horrible. But that's not because of PAT. That's because you have too many people using too small of a pipe. So that piece. And my last rant then, I have one rant I have to put in here. Please, if you set this up, when you set up your DHCPs and you're assigning internal addresses, make them sequential powers of 2. And I say this because when you want to actually manage PAT, if it is not set up with powers of 2, so that means that, you know, 64, something like 64, 96, whatever. If you don't set those ranges in sequential powers of 2, you can never write rules to it to be nice and clean. And it's just my personal rant. If you don't know what I'm talking about there, well, you know, write me an email, I'll explain it. But when you set up DHCP, always use powers of 2. Everybody uses decimal numbers, and I hate it. It drives me crazy because I'm like, don't use 10 to 20. use 16 to 23. Because then when you want to sit down and write rules, you can use binary and you can write these beautiful, clean, nice rules. So, all that said, barring that, the end doesn't come, fire, flood, famine, collapse of civilization, cannibalism, who knows what, by next time, we should be back in the studio next week. We do have some busy stuff coming up over the next while. We may have to record a few more shows, but thanks for joining us on SDL, and I'll see you hopefully live next week, and hopefully Russ will come back stuffed with poutine. Thanks for watching SDL. See ya.